Great. Thanks for the kind introduction. And I would also like to thank the organizers for giving me this opportunity to talk. You're right, Yinje. SKAO stands for Square Kilometer Array Observatory. It's the new branding of SKA, which we're using now. Before I start my talk proper, I'd like to, just remind the participants that this meeting was supposed to be held last year, which coincided with the 60th birthday year of Sunil Maharaj. And although we've lost that opportunity, he is now over 60, it's still a good moment just to wish Sunil happy birthday. Sunil is the founder of gravitational research at the University of KwaZulu-Natal and the longtime director of the research center there. And so congratulations, Sunil, on your amazing contributions to building this group, which today is an internationally recognized research group in gravitation and cosmology. I have the pleasure, or maybe that's a strong word, to have been Sunil's PhD supervisor. And I'm showing you here the first paper that we published together back in the 80s. And finally, here's a picture from 20 years ago, the 3-generation student and supervisor, also in Durban on the occasion of the 16th meeting of the International Society of General Relativity and Gravitation. So that's enough on Sunil, but congratulations to Sunil, and let me now move on to the SKAO topic. So when I talk about next generation galaxy surveys, a number of them spring to mind. In addition to SKA, of course, there's Euclid, the spaceborne survey, which is probably the premier next generation survey. The sky coverage is shown on this cartoon here, and here is an artist's impression of the satellite-based telescope itself. Then there's the dark energy spectroscopic instrument, which is another forefront next generation survey at the Mail Peak Observatory, which is shown in the image here. And of course, the SKAO, which comes in two forms: the mid-frequency telescope on the left, located in South Africa, and the low-frequency telescope on the right, located in Australia. There is, of course, also the legacy survey of space and time being conducted by the Vera Rubin Observatory, shown in the photograph here. And there are a number of others, but that's enough just to give you a general idea of the fantastic new surveys which are coming online in the coming decade. So what are the key things that we're going to be getting from these next generation galaxy surveys? Well, the fact that they map such wide areas of the sky to such deep redshifts means that they will be covering a huge volume of the universe. And this will give them the statistical power to be able to probe dark matter and dark energy with incredible precision. So all the standard cosmology which we've seen conducted by surveys like BOSS and eBOSS will be taken just to another level by these new surveys. And that's really exciting. But that's not all that they will deliver. They will also deliver new probes of the universe by virtue of the fact that they're accessing larger scales than surveys up to now. So if you see on the plot here, the equality scale marks the turnover in the power spectrum, the matter power spectrum. And current surveys are not really measuring as far as this. They're only getting to that just at the boundary of their capabilities. These new surveys will go beyond the turnover and will, in particular, confirm that there is such a turnover. It hasn't been directly confirmed before. But what will that allow them to do? Well, there are a number of things which accessing these ultra-large scales will facilitate. First of all, to probe the primordial universe, which is what our explain and talk about in the rest of my talk shortly. Secondly, another example, they'll be able to probe the statistical isotropy and homogeneity of the universe via the matter distribution, as opposed to the cosmic microwave background. So those are two of the key foundational issues for the standard model of cosmology, which will be opened up by these next generation galaxy surveys. I will just talk about the first one, and of course there's some others which I haven't listed. Lots of exciting new things will be made possible by these surveys. So what in particular does SKAO bring, which Euclid, DESI, LSST, and the others don't bring? Well, simply because it is operating in the radio as opposed to optical and infrared. And the red book produced by the Cosmology Science Working Group of the SKAO, which came out in 2018 or 2019 really, final form, collects together the new science that is realistically forecast to be conducted by the SKAO. And of course, what you first of all will get is just standard cosmology, but from a new angle. So be able to do most of the standard cosmology, galaxy clustering, weak lensing, and so on, but in the radio band, where you have a new angle on things and an independent way of confirming observations that have already been undertaken in the optical. Secondly, the radio surveys are going to cover even larger volumes than the optical infrared ones. So that will give them a certain advantage. And finally, and very importantly, you have completely different systematics in the radio as compared to the optical and infrared. And having these different systematics makes for very powerful cross-checks, and by cross-correlating, very powerful precision as well and new discoveries. Here's just briefly a visual of where the SKAO telescope is located in its two versions. The South African one here is the one I'll be talking about. There is some cosmology possible with the low instrument, but it's kind of a niche area. The main task of the low instrument is to probe the reionization epoch. The real cosmology, and the one I will be talking about, is happening via the mid telescope. Now, the precursor to the SKAO already exists in the form of the Meerkat array, which has been constructed here in South Africa already, consisting of 64 13.5 meter dishes. It's a fantastic telescope. It's been operating since 2019, and it will be absorbed into the SKAO. It's currently probably the world's best radio telescope. Most of what it's done has not been in cosmology because it's easier to do the non-cosmology bits. The cosmology is taking longer to prepare. And the proposed cosmological survey with Meerkat is called MEERKLAS, the Meerkat Large Area Synoptic Survey, led by Mario Santos. I will come back to that a little bit later to tell you about some initial progress towards the MEERKLAS survey that has been proposed. But let me now say something about the foundation for spectroscopic surveys with the SKAO, and this is the neutral hydrogen that exists in the universe. So in this cartoon here, you see the history of the universe, but identifying the genesis and evolution of the neutral hydrogen component. From the Big Bang through the hot plasma era, there was no neutral hydrogen. There were just protons and electrons, but they were unable to combine into neutral hydrogen atoms because of the high temperature. But after the decoupling of matter and radiation, neutral hydrogen formed. The protons were able to combine with the electrons, and there proceeded a period of the dark ages when neutral hydrogen was very slowly giving birth to the first generation of stars. And when those stars formed and lit up the universe, they progressively ionized the neutral hydrogen intergalactic medium until the remaining neutral hydrogen was trapped in galaxies, shielded in galaxies. And SKAO mid is what we would use to actually to detect this neutral hydrogen, whereas the reionization epoch itself will be probed by SKA low. So spectroscopic surveys with the SKA observatory are based on the fact that neutral hydrogen actually emits a radio line called the 21 centimeter line. It's a very weak line, but hydrogen is very abundant. It's the most abundant baryonic element in the universe. And in principle, when you detect a galaxy through the 21 centimeter emission line, you immediately have its redshift. So unlike in an optical survey where you do imaging and then follow up spectroscopy, with H1 spectroscopy, you have detection and spectroscopic measurement simultaneously. And the redshifts are extremely accurate, probably the most accurate redshifts available in the next generation. This 21 centimeter line comes from a spin flip transition in the hydrogen atom, emitting a 21 centimeter wavelength photon in the rest frame. So what will this SKA H1 galaxy redshift survey deliver for us? Well, unfortunately, it's very difficult to measure the emission line, even with a telescope as large as the SKA mid. And it turns out that we will only be able to cover about 5,000 square degrees up to a redshift of about a half using an H1 galaxy redshift survey, simply because it's so hard to detect this emission line. Currently, the emission line has hardly been detected except for extremely low redshift galaxies. But nevertheless, this galaxy redshift survey on the SKA will be a very useful complement to the higher redshift next generation surveys, and it will also overlap with part of DESI, for example. So it will be allow for interesting cross correlations and cross checks and investigation of systematics. This cartoon here shows the galaxy survey's predicted errors for redshift space distortions compared, say, to Euclid. You can see Euclid obviously outperforms it. So is the conclusion that we cannot do transformational cosmology with the SKA? It seems like the disappointing conclusion, and this is actually the situation of about say 8 years ago. This was the general opinion. But in fact, the answer is no, because for a lot of cosmology, we don't need to detect individual galaxies. What we're looking for is the fluctuations that are traced by H1 galaxies on large enough scales to do cosmology. So if we give up the need to resolve individual galaxies and we simply measure the integrated 21 centimeter emission in each pixel, then we create, instead of a map of individual galaxies, which takes a huge amount of time to develop, in a quick time, in principle, we get a map of the large scale fluctuations across the pixels, something like the CMB, but it's like the CMB at a redshift, which you can choose according to the frequency of your receiver. So this allows us to map huge volumes of the universe much more rapidly than an individual galaxy survey would. And in the red book, we've shown that with the high frequency band, i.e. low redshift from 0.1 to 0.6, and the low frequency band 1, the higher redshifts from 0.3 to 3, we would cover a huge volume, a huge range of redshifts. And given that the sky area proposed is 20,000 square degrees, that is the biggest volume proposed for next generation spectroscopic surveys by a long shot. But of course, there is a catch. It's not as good as it may seem from the previous slide. The catch is that foregrounds are much brighter than the signal. This is the same problem as exists for the CMB, but because the frequency is lower than the CMB, the foregrounds are more of a problem. However, a lot of effort has been put into cleaning the CMB signal, and a lot of those techniques can be carried over to 21 centimeter intensity mapping. And already the technology of cleaning methods is quite far advanced, even in advance of the first real measurements of this signal. So the foregrounds, you're seeing here an example of a simulation with foregrounds above, and you can see the scale, the color bar here, in terms of millikelvin, whereas the signal after you've cleaned the foregrounds is down to microkelvin. But this is what we can achieve according to simulations with some of the latest methods in this paper here from last year, Cunnington, Camera, and Port Sudan. So what about intensity mapping with MeerKAT, the precursor of SKAO, which is based here in South Africa? Already pilot surveys have been conducted for intensity mapping. And the hope is that we will make the first detection of the auto power spectrum for intensity mapping. There have been detections in cross-correlation between an intensity map and a galaxy survey, but what we're looking for is the auto power spectrum detection. And as well as having pilot surveys, this requires the building of a complex new pipeline that has never been built before. And this pipeline is being developed. It's at a fairly advanced stage. It's been developed by Mario Santos's group. And here is the key paper led by UWC postdoc Jingying Wang. And here's just a quick cartoon showing some of the complexity of the pipeline that's being developed to deal with the foregrounds and the satellite avoidance and all sorts of other issues that are new issues for cosmology in the field of 21 centimeter intensity mapping. Right, so I won't say more about that, which is very exciting and very important work. I will be looking more to the future when such pipelines have been developed. What will we be able to do in terms of probing the primordial universe using the capacity of the SKAO in combination with other galaxy surveys? So when I say the primordial universe, we want to use galaxy surveys, i.e. use the maps of the galaxy distribution in order to deduce something about the conditions applying during inflation in the very early universe. And what is the connection there? Well, the connection is via the quantum fluctuations that are generated during inflation. These fluctuations are generated on very small and certainly sub-Hubble scales during inflation. And the superluminal expansion happening during inflation rapidly stretches these quantum fluctuations to be super Hubble and to become classical fluctuations. And these are the seeds for what we see in the radiation through the CMB and in galaxy surveys through matter perturbations. The important point that I want to focus on is that these fluctuations are essentially Gaussian for the most simple inflation models, but certainly non-Gaussian for most models, many other models, and multi-field models in particular. So primordial non-Gaussianity, therefore, becomes a powerful probe of inflation. For example, the primordial non-Gaussian parameter FNL, for the simplest kind of non-Gaussianity, if that is measured to be less than or of order 1, this rules out a very large class of multi-field models of inflation. So this could be potentially a powerful probe, the measurement of FNL. And why can we measure FNL? Well, the point is that FNL leaves a trace which is frozen in both the CMB and galaxy surveys in a way that I'll try to explain in the following slides. If we look at this cartoon here of the evolution of dark matter clustering from an n-body simulation, you can see that the development of increasing nonlinearities on small scales here. And the nonlinear growth of perturbations under gravitational instability generates a very strong amount of non-Gaussianity. Non-Gaussianity is effectively nonlinearity. This means that on small scales, the primordial signal, which is much, much weaker, is completely wiped out. So the point is that you need to access the very large scales in the power spectrum, which remain linear and which contain this archaeological signal fossil signal of the primordial non-Gaussianity if it is non-zero. And this is what affects the CMB and the galaxy power spectrum on very large scales. So coming back to our cartoon here, the idea is that non-Gaussianity of some number of FNL is generated during inflation, depending on the model. This is measured through the CMB because it is frozen on the very large scales in the CMB, and then it's measured again at a much lower redshift in galaxy surveys, where the same number is responsible for the signal on ultra large scales here. But as you may expect, this is a very difficult signal to detect, especially in the galaxy survey case, easier with the CMB. So unsurprisingly, the state-of-the-art constraint on this non-Gaussianity parameter is from the Planck satellite. And the latest measurement is -0.9 plus or minus 5.1. In other words, the error, the important thing to focus on here would be the error, is currently of order 5. So future CMB experiments like stage 4 experiments with the CMB will not really improve this significantly. It will maybe by a factor of 2 at most of that order. And that's as much as we'll get out of the CMB. What we really need to do is to use galaxy surveys to help us push down towards 1 and even below 1 for measurement error, for precision on FNL. The first point to make, though, when thinking about this, is that the dark matter power spectrum is not affected on large scales by primordial non-Gaussianity. It is only the bispectrum of dark matter that is affected. It's the same applies to the CMB. Those constraints come from the bispectrum of the CMB. But the key and interesting thing that was discovered just over 10 years ago is that the galaxy power spectrum is affected by primordial non-Gaussianity through the bias of galaxies. And this works as follows. In the Gaussian case where there's no primordial non-Gaussianity, the number density contrast of galaxies in the co-moving frame is equal to the Gaussian bias, which is independent of scale, so it's a function only of Z and not of the wave number, times the co-moving matter density contrast, delta M. Now, what happens with primordial non-Gaussianity is that this scale-independent bias becomes scale-dependent. There's a scale-dependent correction here, which is proportional to FNL times the Hubble rate squared over K squared, the wave number K. And this correction applies when K is less than the equality scale. In other words, it's an ultra-large scale correction to the Gaussian bias. So this fossil signal is what we're talking about. It's sitting in the galaxy distribution via the modification of the bias of galaxies relative to dark matter. And because it only has a non-negligible signal on ultra-large scales, you need ultra-large volumes in your galaxy survey to access this signal. The catch, though, there's always a catch whenever you see a good possibility. The catch is that cosmic variance is growing on these same large scales where the signal of PNG is growing. Cosmic variance simply means, the problem of cosmic variance simply means that in order to measure something on ultra-large scales, you have to measure many, many instances of this, say a separation of 1,000 megaparsecs between galaxies. But there are not that many separations in a galaxy survey. There are many more to 100 megaparsecs separation, and even more 10 megaparsec separation, where cosmic variance is not an issue. But on ultra-large scales, the fact is you don't have enough measurements to get the statistical power to measure the signal you're looking for. Can we find a way around this? Because actually you can show that with a single galaxy survey, you simply don't have the power to constrain FNL in a useful way that's competitive with the CMB. So how do we get around this? Well, we can get around this by combining more than one galaxy survey, provided that the different galaxy survey uses a different tracer of the dark matter distribution. So a different kind of galaxy. This could be, for example, radio survey and an optical survey. They generally they're generally accessing different galaxies, or different traces in different galaxies of the underlying, that trace the underlying dark matter distribution. So in a sense, what you have is the following. You have a realization of the dark matter field with Galaxy Survey 2 and Galaxy Survey 1. And each of them has a different bias, so B1 and B2. And then effectively you take delta 1 over delta 2, and the delta matter multiplying B1 and B2 cancels. So the underlying stochastic dark matter field is cancelled out when you take this division. And so in a sense, you can measure the ratio of the biases without cosmic variance. Of course, one has to take account of the noise. It's not quite as simple as this, but this is the basic idea of the multi-tracer method. And the best results can be obtained if you choose surveys with the most different possible biases. B1 and B2 should be as different as possible. And also with different systematics, because you're going to cross-correlate these signals. We don't just divide them, we actually cross-correlate them and combine that with the autocorrelations. So you want different systematics as well to extract maximum advantage from this multi-tracer method. And of course, you would like the wide sky areas and wide sky area overlaps between these surveys, and you would also like to cover high and low redshift so that you can cover the transition from matter domination to dark energy domination. So I'm going to show you an example which is based on work with my PhD students, Jan Albert Viljoen and postdoc collaborator, Zé Fonseca, in which we use 4 different surveys, 2 from the SKAO, the band 1 and band 2, the low and high frequency bands, and 2 galaxy surveys, a bright galaxy sample from DESI and the spectroscopic H-alpha galaxy survey from Euclid. So these split into 2 pairs. At low redshifts, we have the high frequency or low redshift band IM2 of SKAO, multi-traced with the bright galaxy sample. That's from redshift up to about 1/2. And then at high redshift, we have the low frequency, i.e. high redshift intensity mapping band from SKAO, combined with the Euclid high redshift galaxy survey. And we combine, using the multi-tracer, we're going to combine all 4 of these surveys, as well as doing the 2 pairs. In multi-tracer, we will also combine all 4 together by the multi-tracer method. So let's see what happens. First of all, I'll just make the general point that, as expected, the multi-tracer gives us a huge boost in the precision that we can reach on FNL, as expected, because it's designed to get rid of the problem of cosmic variance, which is what's standing in the way of a precision measurement. And here is a summary of the result, which is in this paper that recently came out on the archive. So in this table here, we've separated out the low redshift surveys on their own, BGS, IM2, and then combined in a multi-tracer. Then the high redshift surveys, the H-alpha and the band 1 of SKAO and the multi-tracer combination. Here you see the actual redshifts if you want to know the values. And then finally, we simply add the 2 multi-tracers, which is what you can do in the Fisher analysis. And then we do the proper full extent multi-tracer combination of all 4. So looking at the errors, the precision that we're getting on FNL here on the right-hand column, you can see that for the low redshift surveys, we're not doing too well. And basically that's because at low redshift, we've not got enough volume to get any kind of reasonable measurement on FNL. This is the cosmic variance problem for a low redshift survey. And you can see that when you combine with a multi-tracer, you get a really stunning improvement in the precision just by getting rid of that cosmic variance. When we go to the high redshift surveys, the measurements are better because of the volume accessed by these surveys. But still, the multi-tracer combination gives you a significant major improvement. And then when you go to the full combination, when you combine both of these pairs, we get down to 1.54, which is extremely impressive. It's not yet below 1, but it's just a very good illustration of the power of the multi-tracer method when trying to pick out a signal in the galaxy distribution on very large scales, such as the primordial non-Gaussianity signal. So I'll come back to how we can get below 1, but I first want to deal with an important issue that arises when dealing with an ultra-large scale measurement in a galaxy survey. So if you think about what we're doing when we count galaxies, say, or when we measure intensity mapping, we're covering correlations which can go across very wide angles across the sky. We're covering correlations which go deep in redshift so that the effect of lensing magnification becomes non-negligible. And we're covering correlations where there are other effects such as Doppler effects and Sachs-Wolf type effects, which also can become non-negligible on these very large scales. So in order to have theoretical accuracy as opposed to precision, precision is the size of your errors, the accuracy is the accuracy of the correctness of your model. Are you taking into account all the theoretical effects, forgetting the experimental effects, but all the theoretical effects that you need to take into account in a very large survey? So in summary here, the effects we need to take into account: wide-angle correlations, lensing magnification effects on number counts, and other relativistic effects, including particularly Doppler effects. So here I've shown schematically, this is the observed number density contrast. This is the number density contrast at the galaxies without observational effects, but we can't measure this quantity here. The quantity is modulated, the quantity at the source is modulated first of all by the linear Kaiser redshift space distortion effect over here, which is the radial gradient of the peculiar velocity radial component. So n is the line of sight unit direction, and v is the peculiar velocity of the galaxy. So this is the Kaiser term. Here is the Doppler term, which is not the gradient of v dot n, but v dot n itself with some coefficient. The lensing magnification term is in terms of kappa, which is the lensing convergence itself, and that's a line of sight integral over the matter density between the galaxy and the observer. And S is the lensing magnification bias. And then there are a few other terms I've omitted here, which are to do with Sachs-Wolf, integrated Sachs-Wolf, and time delay terms. So theoretical accuracy requires us, in principle, to include all of these terms in our modeling, which is exactly what we did do in the results I've shown you. Now, if you use a standard power spectrum analysis in Fourier space, none of these effects is included. You can include wide-angle correlations, but in a perturbative sense, and you can include the Doppler term, but without full wide-angle correlations, and that's a bit of a problem because the two things tend to cancel each other at some level. And you can't really include lensing magnification in Fourier space. I mean, there are ways around this and people are developing it, but it's very difficult. And there's another way which avoids the problems posed by trying to tackle these issues in Fourier space by just abandoning Fourier space and going into angular harmonic space. And if we look at the angular power spectrum, it naturally includes all of these effects. You don't have to make any assumptions or approximations. You don't have to do any add-ons. It's simply everything is there. Of course, it has its problems, but like everything, there's a catch. So the angular power spectrum is defined by the redshift or the light cone observed correlation function, which I'm shown on the left here. So that capital delta G includes all the terms I was talking about. And all wide angle correlations are permitted, so there's no restriction on the cosine of the angle of ni dot nj. If you expand this redshift space correlation function in angular harmonic space using the Legendre polynomials, you get the angular power spectra. So this angular power spectrum isn't observable. The spatial power spectrum is not observable because the spatial power spectrum tells us about three-dimensional hypersurfaces of constant redshift, and that is something we cannot observe. We only observe on two spheres that intersect this three-dimensional power spectrum. It doesn't mean you cannot use the power spectrum, it just is not directly observable. And in particular, if you do use the power spectrum for your analysis, you have to have an Alcock-Paczynski correction because you need to assume a model in order to interpret your data. Whereas since CL is observable, you do not need to assume any cosmological background model in order to interpret your data or to model your data. It isn't observable. So, what is the consequence of neglecting lensing and other relativistic effects in the analysis of the power spectrum? I've shown you here the dramatic consequence of it. If you neglect these effects, then you will introduce a theoretical bias, a theoretical systematic. And that systematic affects the best fit measurements or the best fit values that you predict for your parameter. And in this case, the parameter we're looking at is FNL. And so when you neglect lensing and the other relativistic effects, you're inevitably going to have a bias on the best fit measurement of FNL. Now that bias may be very tiny, and then you could say, well, although that's theoretically the correct model, we can just forget it because the consequences of forgetting it are unmeasurable. But what happens here in the case of the 4 surveys that I've been talking about, you can see that there's a very real bias. The only case in which there isn't a bias is the low redshift combination of IM2 and BGS. You can see that the fiducial value of FNL, which I've marked here in the crosshairs of the 2 dotted lines, is still contained in the 1 sigma contour of the low redshift combination. But as soon as we include the high redshift combination, the high redshift survey combinations, you can see that we're going progressively further away, and then the full multi-tracer combination pulls us back a little bit here. So the bias on the best fit here has become so large that in a Gaussian universe, which is the fiducial model here, so in this case, we've got a Gaussian universe, but by neglecting lensing and the other relativistic effects, we would deduce that we have a universe with FNL of order 5. So in other words, we would deduce that our Gaussian universe is actually non-Gaussian. That's quite a serious error to make. So when going after a parameter such as FNL, whose signal exists on very large scales, the lesson here is that you have to be very careful not to omit the large-scale effects that modulate the galaxy number density contrast and the intensity mapping temperature contrast. So I said I would come back to the question of can we get below 1? It turns out that the way to optimize your multi-tracer, the final step is really to use a photometric galaxy survey, such as LSST, which has a much higher number density than the spectroscopic survey of Euclid. It turns out that the redshift accuracy is not as important as the number density. So if we replace Euclid by LSST, we can go down to 0.68 for our error. This is actually shown in the Cosmology Red Book. And this is just using the combination of SKAO and LSST. In fact, if we add now a third tracer by having not just LSST, but another galaxy survey, potentially Euclid itself, we would be able to go even further below 1 than 0.68. And this is work in progress.
I would like to remind Roy for, I think, just if you could finish in a few minutes, that's would be better. Thank you.
That's no problem. I'm just about there. In fact, I am there. So I'll just show you in closing a couple of impressive pictures about the construction phase of Meerkat. Here, for example, is the underground computing facility, a massive supercomputer sitting under there. There's a nice image showing, there's an image in the background that comes from Meerkat. And here, just for interest, showing you where an upgrade of SKA in phase 2, which is a futuristic version of SKA, will extend the dishes into the 8 partner countries. And an old obsolete telecommunications dish in Ghana has already been converted into a radio telescope to help train people in anticipation of this fantastic development. But yes, let me end there and welcome any questions.
Okay, thank